your CO2 emissions, which I put there as a number as 210 tons of reduced CO2 emissions by switching to a biocarbon product. What I'm submitting to you is that you can work out for yourself the carbon footprint calculation, saying, today I use a petrol feedstock and my carbon footprint is X. By switching to a bio feedstock, I can eliminate this X, and the value is 0 if I start. However, to convert that feedstock to my product, I'm going to use carbon energy, I'm going to put out carbon emissions. What is that value? And that value, if it is less than X, which is what your current petrol feedstock is, then you have a viable route to switching to a bio feedstock and thereby reducing your carbon footprint and your total environmental footprint as well. That's what the message I'm conveying to you as part of this presentation. All right, so then go to the slide number 13, and we talked about bio. We are saying bio has a value proposition, and you have to ask the question, how does one identify and quantify this biocarbon product? How do you define a biocarbon product? And this is why we have given a lot of our contribution in this field, if you want to state it, and they are in the the references which I have shown in the slide. Let's forget that for the minute. So we want to know how to identify and quantify biocarbon product. So in this slide, we are going to address that. So fortunately for us, in the atmosphere, carbon-12 is in dynamic equilibrium with radioactive carbon, as you can see in that slide. The half-life of radioactive carbon is 5,700 years. When this inorganic carbon is converted to organic carbon, as you can see, the biomass or the bioorganic carbon will still have that radioactive carbon signature associated with it, right? Its still half-life is 5,000 years. But the formation of fossil resources is in millions of years. So as you can see, the fossil resources does not have any radioactive carbon signature associated with it. So it's a very simple, elegant way to quantify bio content. And we have now codified this into an ASTM standard, ASTM D6866, and the carbon-14 signature forms the basis of it. So I'll take the product and I'll talk about it in a minute, but new carbon versus old carbon. This will have no radioactive carbon signature associated with it, the fossil carbon, and the biocarbon will have a radioactive signature associated with it. So, some fundamentals. Take a carbon product, you combust it to CO2, you measure the carbon-14 carbon-12 ratio, you compare it directly to a standard oxalic acid new carbon product, 100% biocarbon product, and therefore you can calculate the amount of biocarbon present in your product. We even correct for the bomb correction factor by multiplying by 0.93. If you remember, in the 1950s, we had exploded a lot of nuclear bombs into the atmosphere, so the amount of radioactive carbon in the atmosphere increased, and we are correcting for that as shown there. I'll skip this, and bottom line, for those of you who are interested, the oxalic acid standard used is an SRN 4905, and the total value, absolute value, is 14.27 disintegrations per minute per gram is the absolute value of that oxalic acid standard. So if you had 100% bio content and you burn carbon to CO2 and you measure the disintegrations per minute per gram, you'd get 14.27. If it was 50%, then you get half of that. So that's how it is done. So it's a very simple way to do that. All right. So go to the next slide. And this slide just summarizes the ASTM method to determine the biocarbon content, or to measure the radiocarbon content. And there's method A, method C, method B. I'm not going to go into the details, just put it up there for you, to suggest to you that the precision on this is 2% or less. So I can get a absolute biocarbon content determination plus or minus 2%. Okay? So, the next slide, which you have in front of you, is to determine the amount of bio-content or bio-based content of your product. And what you have on your slide, you can see, is the percent bio or bio-based content is the biocarbon divided by the total organic carbon as a percentage. So bio content is basically biocarbon content, all right? And you can see that on a carbon basis. It's not on a weight basis or a mole basis or any other measure. So think for a minute. If I determine my biocarbon content, I can translate it directly into the CO2 emissions reductions that I can achieve. All right? Let's put this into an example, which is what you have in front of you. Let's say you have a product N, which is a fiber-reinforced biocomposite, 30% fiber, which is cellulose, 70% polypropylene. On a weight basis, people will say, well, this is 30% renewable content, and many companies still do that. However, on a carbon basis, it is only 18.5%. Why? Because remember, it is on a carbon basis. So, how do we get this number? You have 30% of biofiber, so 0.3 times 45.5, which is a percent carbon in the cellulose. That's your biocarbon, divided by the total organic carbon, which is 0.3 times 45, plus 0.7 times 85.7, 85.7 being the percent carbon in polypropylene. So biocarbon divided by total organic carbon, and the percentage is 18.5. So this is how we compute the bio content of the product. All right. So the terminology then becomes very simple. A bioplastic or a bio-based material is an organic material in which the carbon comes from new carbon. So basically a bio-based product has new carbon. It must also be an organic material. So remember, we are not talking about inorganic material. So for example, we're not talking about calcium carbonate and asking the question, is that carbonate bio-based or not bio-based? So many of you use calcium carbonate as fillers in plastics. That's not a bio-based value proposition in the context of what we have been talking about so far, right? But if you want to call something bio or bio-based, it must be organic and must contain new carbon. That's the fundamental basis for this value proposition. All right. So this bio-based content determination I've talked about is also applicable in the energy and fuels area. So we can use the same discussion for computing how much of renewable energy, if you mix, for example, partly bio and partly fossil-based fuels, you can also calculate how much biocarbon content there is, and therefore how much is your reduction of your carbon footprint. Now let's switch gears and say you're convinced you want to look at bio-feedstocks and your ability to use that bio-feedstock to make product. So here is your choices. If you look at bio-feedstocks, you can have what I call cellulosics and lignocellulosic. These are polymers. I'm going to skip this except to show you that these are the products one can make out of this. The ones in green in front of you are products which is being worked on in my laboratory, and that's just information for you. So you can have a cellulosic feedstock. You can use natural fibers like kenaf, jute, and using biofiber composites, and this is commercial. You can use starches, and you know this is being commercial also. You can use other polysaccharides. Examples are given there. You can use fats and oils. This vegetable oil as a platform for making all sorts of products is possible. And you can use soybean and all the other products which you see listed there. And you can use protein. But these are direct polymers, so you have to actually work with a cellulosic polymer or a starch polymer or a biopolymer. The other alternative, which is being proposed in a very big way, is to hydrolyze the renewable feedstock to form what I call biomonomers. This biomonomers, so basically sugar or glucose, which is what you form out of the carbohydrate feedstock. This biomonomer can be fermented by bioprocesses to give you things like succinic acid, adipic acid, 1,3-propane-diol, and you can form polyesters. Classic example here is the DuPont Sorona polymer, which is based on 1,3-propane-diol and the succinic acid, 1,3-propane-diol and terephthalic acid to give you a biopolyester, right? It follows the fermentation to 1,3-propane-diol, which you see on your slide. Another very successful example is the converting the biomonomer to lactic acid, to polylactic acid, and all the products one can make out of it. This is the NatureWorks technology. And there are other producers of lactic to PLA. You also can take the monomer and produce what is called as polyhydroxyalkanoates. It's shown in blue on your screen. These are the microbial polymers and commercialized by now Metabolics and ADM in a joint venture, and again a bio-based plastic material. More recently, we'll talk about that in a minute, but you can also hydrolyze or go through chemical process. It doesn't have to be a biological process. You can take the vegetable oil as your platform and then convert it into you can take vegetable oils and you can make your polyesters and polyamides. All right? So that's your value proposition over there. Okay, so now let's go further and look at the next slide, which is the, give me a minute here. So, you can make all these macromers, and the more important part I wanted to bring out to you here is the fact that recently Braskem announced making polyethylene from a biorenewable feedstock. So what you have there is converting sugarcane to ethanol, which is then goes through the standard process, make ethylene out of ethanol, and then follow traditional polyethylene. So you have a biopolyethylene feedstock over there. All right? So this is the potential and possibilities you have over there. Now, what about biodegradability? Is that an important issue also? As we talked about, biodegradability has nothing to do with bio-based. It has got to do with end-of-life option. And this involves complete removal from the environment of your product in a safe and efficacious manner. And it enters into the microbial food chain. The key take-home message is as follows. When you